Okay, so now we're going to look at the common gate amplifier, and by now you should know how it goes. So in particular, first we need to solve for a DC bias point. So for a common gate amplifier, that involves opening all capacitors. This is open, this is an open, this is an open, and lo and behold, we are left with the same exact circuit we've had for the past two amplifiers, our 4-resistor bias network. Then you have to basically, once you have extracted this 4-resistor bias network, you need to analyze it. And so here I write down the analysis. And then once you have the value for ID, you're going to plug it into your equation for GM and your equation for RO. And now you're ready to solve for the small signal model. So to derive your small signal model, so we must first inactivate all DC voltage sources. So V plus becomes a ground, V minus becomes a ground. Additionally, we must short all capacitors. So this becomes a ground, this becomes a ground, and this becomes a ground. So you notice our gate is grounded. So we're going to put it at the bottom on our circuit, our pi model. And our input side is actually the source. So we have the source here. And our output side is actually the drain. And so we always have a current source pointing from the drain to the source. And that's going to be GM, VGS. And in parallel to that, we have our little RO. In general, for per the textbook, when we analyze this common gate amplifier, we're always going to assume there's no channel length modulation. And in that particular case, RO will always be infinite. And so we can neglect it. So we don't need to keep it in our circuit model, but for now, I'm just going to keep it there. Okay, so now let's go terminal by terminal. So we have that R2 is connected to ground on one side and ground on the other. So it's actually shorted. And same thing happens to R1. It's connected to ground on one side and ground on the other. So it's also shorted, so it doesn't have to be added to our circuit model. So we're just left with the ground located at the gate. Now we go to our source terminal. And our source terminal has RSS connected to it, which is then connected to ground. And then it's got R sig, which is then connected to V sig and then to ground. Which is then connected to V sig and then ground. And then finally, we have RL, which is just connected to the drain and then ground. And we have RD, which is connected to the drain and then ground. And then this is our output voltage Vout. Okay, so now we have our small signal model. In the next slide, I draw it more cleanly. And now we're actually going to derive what AV, AVI, RO, and RIS is. And we're always going to assume lambda is 0 because that's what the book does. So we will actually remove this RO from our following circuits. So this is the circuit we need to analyze. And we need to come up with the gain, or V out over V in. So AV, which is equal to V out over V in. And to do that, we need to figure out how much current is flowing here. We'll notice that the voltage VSG is actually equal to V in is equal to VSG, which is actually equal to V negative VGS. So that means that this current source is actually GM, negative GM, VN. Okay, now let's look at this node equation. So we have currents coming in this direction. So we have negative GM V in plus 1 over RD plus 1 over RL V out have to be equal to 0. And that's just going to give us what our gain is, which is just basically V out over V in equals GM times 1 over RD plus 1 over RL to the negative 1 power. So that's how we derive AV. Note that this would be a lot more complicated if we actually had that RO in parallel, and that's probably why the book doesn't neglect the RO in parallel. Okay, so now let's look at our next example. But before we do, I guess here I wrote it more cleanly. So that's the nodal equation. And then we're going to plug in negative B in for VGS. So once we have it, V out equals GM VGS times this. We're going to replace negative B in here. And that will give us kind of two negatives become positive. And then you just divide out by Vn to get this. All right. So just like all of our other circuits, now what we need to do is define an equivalent circuit where we're going to connect R sig to this and then V sig to this. And then on the other side, we're going to connect RL, and then this is V out. So to find the intrinsic properties, we're going to remove RL, or treat it as infinite, and remove R sig and V sig. And this will be our input, and this will be our output. So that's what I show in this next slide. So we just opened our load, and then we remove the V sig and R sig. So now we're going to find. Okay, so to figure out this gain, we still have that Vn is VSG. So Vn equals VSG, which means that, which is negative VGS. So now that we know that Vn is equal to negative VGS, we now need to figure out, we now apply KCL at this node. And so we have GM times negative Vn plus V out over RD equals 0, which gives us that V out over RD equals GM V in, and then that's going to give us that V out over V in equals GM RD. So that's it. That's the gain of the common gain amplifier. In the next slide, it's summarized and typed up. So let's go to the next slide. So here's the gain of the open of the common gate amplifier. And again, you derive the nodal equation for this node. So we have V out over RD plus GM VGS. And that allows us to say that V out equals negative GM VGS times RD. Then for VGS, we plug in negative V in. And then that gives us this. And then we divide both sides by V in to get that AVI is equal to GM RD. All right, so let's do the next slide. Okay, so to find the output resistance, we set V in to 0. Well, if V in is 0, that means that VSG is equal to 0, which is equal to VGS. So as a result, nothing will flow through here because this is just going to be 0. And so when we do an IX VX test, so if I plug in VX here, IX will be equal to, will all flow through here. So we're going to get that Vx over Rd equals Ix, which tells us that Vx over Ix equals Rd. Now, I know in 2K1 they used 1 volt source here. I'm going to use a 1 volt source here. So then I'm going to get that the voltage drop across Rd is just going to be 1 over Rd, and then 1 over Ix is going to be equal to Rd. So I'm going to get that R out equals RD. So this derivation is kind of repeated here, and we get that R out equals RD. You could have also done this by inspection. Since there is no current flowing across this, since VGS is 0, there's no current flowing through this branch, and so your only output resistor is RD. Okay, so now we're gonna do another IXPX test. So in this particular case, we still have that VSG equals to Vn, which in this particular case we set as Vx, which means that VGS is actually equal to negative Vx. So we need to figure out what Ix is. So if Ix is coming into here, we have this current in the opposite direction, so negative Gm VGS, and then we're going to have another current, which is just Vx over RSS, or Vn over RSS, which is here. And then we are going to replace this VGS with negative Vx. So that's going to give us 1 over RSS plus Gm times Vx equals Ix. And then the ratio of Vx over Ix would just be 1 over RSS plus Gm to the negative 1. And that's equivalent to saying that the input resistance is just RSS in parallel with 1 over Gm. So remember that Gm is just equal to 1 over Gm. Okay, so that's the input resistance, and that concludes this particular lecture. So remember in 2K1, you were told to just put a 1 volt test source. Well, that would make this into a 1. That would make this into a 1. This would become a negative 1. So this would be actually a 1. And then you would compute 1 over Ix, which would give you the exact same thing. So it doesn't matter whether you plug in Vx or Ix or 1 as your test source, as long as your output is Vx over Ix or 1 over Ix. So this is if the test source is Vx and if the test source is 1, you will always get the right answer for your input resistance. Okay, so that concludes our common gate analysis. So I'll summarize the results in the other slide. Okay, so now I'm going to summarize in this final slide. So in particular, for this particular circuit, again, our final results are that the input resistance is RSS in parallel to 1 over Gm. Our output resistance is RD, and our gain is Gm times RD, and our open gain is Gm times RD, and our non-open gain, or when we include RL into our gain, is just Gm times RD in parallel with RL. So believe it or not, we're basically done with this lecture, and that concludes our analysis of amplifier circuits. We've derived every equation in the book. And for your exam, you should know how to derive any of these parameters for all 3 circuits. And we might actually give you some different ones. When we give you different ones in an exam, though, they are usually slightly simpler than the ones in the textbook. Our goal is to make sure that you know how to apply this most signal analysis. In next class, we're actually going to look at our low and high frequency analysis, and that will conclude our MOSFETs for this particular class.